Hi, and welcome to this video which shows you how to do a KC calculation of a Year 13 or an A-level demand type question. This one is one of the ones on the worksheet, and it's question 1 on the worksheet. And in this question we're being told about an equilibrium between ethanoic acid and ethanol that are reacting together to make ester and water. The ester, by the way, is called ethyl ethanoate, and they give it that name in the question. Now, this this reaction is reversible. So if we do this chemical reaction in a vessel where we add 2 moles of the alcohol and 1 mole of the carboxylic acid, and we put a cork in the top to seal the bottle, that this system will reach equilibrium. And slowly, as it reaches equilibrium, the amounts in there will go down. These things will react together to form some of this, but it won't go 100% because some of these products react together to go back again. In the end, you reach a point where the rates of the forward and reverse reactions are the same. When the rates of the forward and reverse reactions are the same, you have reached a point called equilibrium. Now, it is called dynamic equilibrium because the 2 reactions, forward and reverse, are still going on at a steady rate. But because they're going on at the same rate, the amounts, the moles of all the chemicals no longer change. Now, what we know, according to the question, is if we start off with these amounts, 2 moles of that and 1 mole of that, that you're going to end up with 0.845 moles of the ester. So all I've done is I've taken the blurb from the question and turned it into 2 little pictures that help me think about equilibrium and what happens when chemical systems reach equilibrium. The problem we're being asked to solve is the numerical value of the equilibrium constant Kc. So I'm going to do this problem in 2 steps. Step number 1, I need to work out the number of moles of all 4 things at equilibrium. Step number 2, I need to write an expression for Kc and substitute the numbers in. So let's go with those 2 steps. So in this part of the calculation, I am using this technique. Initial, as in the initial number of moles added to the reaction vessel, the change, how much they've gone up or down by, and the final amounts, the equilibrium amounts, ICE, sometimes called the ICE method. So I've taken this information from the question blurb that there were 2 moles of alcohol and 1 mole of carboxylic acid, and I know that when we reached equilibrium that the amount of ester was 0.845 moles. Now I can use that number to work out the other 3 numbers in the bottom line, and I do that by using this middle line, the change. You see, if there was no ester at the beginning and now there's this much ester, then the amount of ester has gone up by that much. Well, since this is in a 1-to-1 ratio, therefore I must also have gone up by the same number of moles with respect to the water. 0 plus this number gives 0.845 moles, and I know the number of moles of water at equilibrium. Meanwhile, over here, how do we find these numbers? Well, this is not a mathematics lesson, it's a chemistry lesson. So think chemically about what happened. Where did the ester come from? It came from the reaction of these 2 guys who came together to make the ester. So therefore, these amounts must have gone down because those amounts have gone up. And since everybody is in a 1-to-1-to-1-to-1 ratio, they've gone down by the same number of moles as that went up by. 1 minus 0.845 is 0.155. 2 minus 0.845 is 1.155. And I have the 4 equilibrium amounts ready to put into my expression for Kc. which is the next and the final step of the calculation. So to do the final bit of the calculation, here are the 4 moles that we've just worked out, and I need to put these into an expression for Kc. So Kc is equal to the concentration of the product, so the concentration of the ester multiplied by, not added, multiplied by, the concentration of the water divided by the concentration of the reactants, concentration of the ethanoic acids, multiplied by the concentration of the alcohol. Now I've got that expression, I can substitute in the numbers. 0.845 for the ester, multiplied by 0.845 for the water, divided by 0.155 times 1.155 for the alcohol. So let's put these numbers into our calculator. Now, as you put the numbers into the calculator, you can probably imagine that we're going to end up with a lot of significant figures in our answer. Well, we can deal with those significant figures if we remember that an answer should not be quoted to more significant figures than the original data. So my answer is 3.9884094. Yet my numbers are only ever given to 3 significant figures. I mean, that one's to 4 significant figures, but it doesn't matter because the limiting factor is the one to the least number of significant figures, which is that. So therefore, to 3 significant figures, this is 3.99. So that's the value. What about the units? Moles per decimetre cubed times moles per decimetre cubed is moles squared dm to the minus 6. Moles per decimetre cubed times moles per decimetre cubed is moles squared dm to the minus 6. And don't take a genius to work out. You're going to cancel out. You're going to cancel out. And this number has no units. It is a unitless answer. Now, what I'm asking you to do today, in order to go on to harder Kc calculations, is to do the worksheet following this model of how you solve these problems. Because over the coming week, and over next week as well, we'll see that when you start to meet equilibria where everything is not in the same state, what are called heterogeneous equilibria, the picture is more complicated. And then we finish the topic by looking at what's called Kp. And Kp, the P stands for pressure, because we look at gas-based equilibria, and these require further steps. But it's very hard to do those further steps until you're confident in this method and how it's done. And that is why I'm passing you these calculations for you to do today. Okay? So very best of luck, and I hope to see you all in the near future.